Hello everyone, welcome to COM 371 at Concordia University. This is the last video from the video sequence on how to make graphics fast. The previous two videos we looked first at methods how to simplify the number of primitives to render with fewer primitives. For the same quality we introduced some faster techniques which give us similar results. Then in the second part we look at culling techniques where we have two types of strategies. One is the bounding volumes where we cover our model with a simple object that we can test. We can do conservative fast testing to prune certain rays in the context of the ray tracer. And today we're going to look at the second one, which is the space partitioning. So whereas in the bounding volume we focused on the objects, now we are focusing on the rendering space. We are going to structure our space in a way that makes the rendering faster, more efficient. We're going to look at three different techniques. So the first one is going to be the space partitioning with a regular grid. So this is something that is very commonly done in graphics in multiple contexts, but essentially what it is you partition your rendering volume in a 3D grid, and you use this grid to shoot the ray. So for example, in this example shown here, you have a ray entering at this point here into this voxel. Of course this is a 2D example, but the same thing works in 3D. And so it's easy to detect, let's call them voxels or cubes. So in these voxels, when the ray enters, you know exactly, based on the direction of the ray and based on the intersection point, you know exactly, you can compute very efficiently where is it going to exit, and based on where it exits, you know the next cube and so on and so forth. So essentially, you can trace the ray simply by tracing the cubes that are intersecting. And the good thing about doing that is that you only need to intersect your ray with the objects inside these cubes. So this is, and then we don't have to worry about the ordering, because once you intersect something, you know it's the closest to you because it's in a cube which is closer to you than the other cube. So we don't have to intersect with everything. The first time we intersect something, we can stop. This is one advantage, and the second advantage is that we can very easily attach to each voxel the primitives such as triangles or the objects which intersect with this voxel. So we can only intersect the ray with a few triangles. So even if I enter this voxel here, for example, I only have to intersect with a few triangles, not the entire model. And then I can stop if something intersects, so I don't have to even move forward to see. So the combination of these two things makes it very efficient. And I'm gonna explain this in more detail at the end of this video, because it's a very interesting algorithm, and it's the same algorithm that you use for linear rasterization. So it sort of goes in multiple, this algorithm can go in multiple topics in computer graphics. As you can imagine, this is how you would rasterize a line on a 2D screen in the exact same way. So what is the disadvantage though of this method? Well, let's wait for another few seconds to see if you figure it out, but I'm sure some of you will. The problem with a regular grid is very memory intensive. So a memory grid has an order n cube of voxels, which is a very high order. So even a small volume, the cubes have to be pretty large to be able to fit in memory. And this is not even the problem. The problem is many of the cubes are gonna be empty, and this is because look, all these cubes here are completely empty, right? So we allocate this large space, and then most of it is empty. So this makes it very inefficient. So there's no surprise. Then we can go for something which is a little bit more memory efficient, which are different types of special partitioning trees, and we're going to look at three of them. The first one, we're going to look at binary space partition, or BSP trees. This is a method which used to be very, very popular at the beginning of computer graphics. And it has a fairly simple principle, is that I divide my space into two using planes. Why planes? Because planes are very efficient to compute the intersection with, right? Or to see if they're visible. This BSP trees, by the way, is used mostly for real-time rendering, not so much for ray tracing. So you partition it in multiple ways, and then you can easily check which of these partitions are in your viewing frustum. But that's not where the gain is. The gain is that this gives you an ordering of the triangle. So one of the problems when you render a lot of triangles comes from the fact that you render a million triangles, but at the end you get only that many pixels on the screen. So many of those triangles you render, they are overlapping. So we discussed this a little bit when we discussed about culling, that sometimes maybe we can do some fragment culling, like we can remove the fragments we don't have to compute the shader for the fragments that are going to be in the back. But this is a little bit difficult to do on a fragment level, so the BSP trees are trying to do it at the primitive level, which is a triangle. So what happens in fact with BSP trees is it gives you based on this partitioning, it gives you the correct ordering. So you can already render the triangles which are going to be in front, and doing that saves a lot of time later. So the BSP trees have several ways in which they can optimize, but this is their main optimization gain, by selecting only the vertices which are already in front of you, and they do this using this binary, this hierarchy of planes. So unfortunately, BSP trees are not. They're expensive to compute. They're expensive to compute optimally, and they're only work if the scene is static. And now, as you know, most of our scenes are not static at all. So this is why, in practice, they are only used basically for the static part of the scene, right? So if you have a lot of terrain, if you have a lot of objects, buildings, so when you have large objects that are not anymore, they're not moving anywhere, and they're static, then you can have, so basically for the environment, do it from the environment geometry, because you compute it once, and then you can load them together with you load the BSP trees as part of the asset, which the asset here is the environment geometry. But you cannot really apply it for any object that moves around, and this is why their impact, they're not anymore, and especially with the high speed rendering, they're not used a lot. Their gain is a lot reduced. So as I said, they're mostly used now for the static part of large worlds, where it still makes sense to use them, because a world can have so many triangles, and some of them are hidden by others, right? So you can have a building, and then behind of the building I have another building, right? So I really don't want to. I really don't want to render the other building, right? So if I have one of these binary partition planes in between, then I'm not going to even go there. So this is sort of the logic behind it. So, but if you go back to the if you go back to the ray tracer based space partitioning, we have two types of trees: quad/oct trees and Cayley trees. So let's start with the quad tree oct tree. So the reason why it's called quad tree oct tree is because in 2D it's a quad tree, which means that you start with your scene as one voxel, and then depending on where your geometry is, you subdivide. So the children of this tree you subdivide into 4, and you subdivide it exactly in the middle. So you subdivide it in 4 quad. In 3D, of course, it's going to be an oct tree, because when you subdivide the voxel, you subdivide it in 8, so it has 8 children. And so, and then after, so in this case we have a circle, so we subdivided this voxel here, has nothing, so we never have to subdivide it. So you can see already why this is efficient, more efficient than the grid, because now large spaces which are unoccupied we can leave empty, so we don't have to physically have voxels there, which saves a lot on the memory. And then, as you see, we can do it again. Unfortunately, this circle spans the three other voxels, so we have to do subdivision on them, and then we do it, and then we have to do this multiple times until we have the resolution that we want. Basically, so we can choose what resolution, what the condition for stopping this tree building. As you can imagine, we want to have we don't want to have too much depth, because when we use this tree, usually we have a log n factor, right? We start at the root, which is the entire space, and then we go down some branch. So if we have too much depth, then this is going to be time consuming. So of course it's log n the space, so it's not the concern I mean, still it's a log n factor, so it's fast, but deciding where to stop, it sort of impacts the performance, so you have to see a little bit better how you do that. The quad tree, occ tree are very simple to build, right? They're simple to build because you always do it in half. But as you can imagine, they're not so efficient, because, for example, here we have these voxels and this one here that they're unused, but still there are 4 empty voxels, and we have here 2 empty voxels, and we have here 2 empty voxels. The quad tree are still not, they can still be optimized a little bit, but they're nice and easy to implement, so this is why sometimes people do it. The alternative to quad trees, occ trees, is the KD tree. So the KD tree uses the same idea, so it's subdivision of the space, but you don't do it both in X, Y, and Z at the same time. You do it in one direction at a time. So for example, here you see this is the first partitioning, so you have only 2 children, right? And then you have another partitioning here, right? And you have another partitioning here. So you have, every time you partition once. And also the partitions are not anymore cubes, which this can create a little bit more complexity, more computation when you're going to try to intersect, because you still need to take the ray and you want to traverse through this tree. So in the grid, you traverse the voxels, you do some sort of rasterization. Here, the ray goes into the root, which is the entire volume, and then you have to figure out which voxel it traverses. So this means you have to do some traversal of this tree, and it might be simpler if everything is a cube, as it was okay before. So all these things here have pros and cons. So it's really a question of how what pros and cons are good for your own case that you're working on, right? So it's not very clear. There's no one universal solution which is used by everybody. In that sense, I would say that KD trees are the most used in practice. So we're going to look later on at an example of how a space partitioning using KD trees for a ray tracer would work. But occ trees and quad trees are also used a lot, and also the space partitioning with the grid, it's also used. So I'm going to go into more details in the following videos on how the space partitioning works. It's very cool, actually, and briefly about how the KD tree partitioning works for a ray tracer.